All right, final exams. They're right around the corner, and I know the pressure is probably building. But hey, don't sweat it. You've totally got this. Think of this as your last-minute, super-focused cram session for applications generation. We're going to make sure these key concepts are locked in so you can walk into that exam feeling totally confident. Ready? Let's do this.
Okay, so here's our game plan, our study guide for this session. We're going to start with the two big categories of software. Then we'll dive into system utilities, the tools that keep things running. After that, it's the big one, open source versus closed. Then we'll get into how your code actually gets translated for the computer to understand, look at the 4 stages of compilation, and wrap it all up with how everything gets linked together. Let's jump right in.
All right, first things first. This is one of those concepts I can pretty much guarantee you'll see on the exam. The 2 main categories of software. Seriously, if you get this down, everything else we talk about is going to make so much more sense. It's the foundation.
So that first category, that's application software. This is all the stuff you actually use day to day. Think about it. Your web browser, that game you're addicted to, a word processor, a photo editor, anything that's designed for you, the user, to do one specific thing. Simple as that.
And then, on the other side of the coin, you've got systems software. This is the stuff that works behind the scenes. It's the powerhouse, the stage crew. It runs the computer itself so that all your applications have a platform to work on. Your operating system, like Windows or Mac OS, that's the biggest example. But it also includes things like device drivers and all those little utility programs that just keep things humming along.
And this is really the key takeaway here. Look at the relationship. Application software is what you see, it's what you use, but, and this is critical, it completely depends on the system software. You literally cannot run your web browser without an operating system. So the system software is focused on the hardware, making the computer work so the applications have somewhere to, well, run. They're a team, for sure.
Okay, quick pop quiz for you. Pause if you need to. Can you name 2 examples of each type of software? And the big one, which one needs the other to run? Get this right, and that's an easy point on the exam, I promise.
So, a minute ago I mentioned utilities as part of system software, right? Let's zoom in on that a bit. Think of these as the essential maintenance crew for your computer. They're the tools that keep your system healthy and running smoothly.
Okay, these 5 are the ones you absolutely have to know. Compression, it shrinks your files down. Disk defragmentation, that one tidies up your hard drive, kind of like organizing a messy bookshelf, so you can find things faster. Antivirus is your digital bodyguard, protecting you from threats. Automatic updating is super important. It patches up security flaws. And backup, well, that's your safety net, your uh-oh button for when things go wrong. Each one has a really vital job.
All right, another quick check-in. Which one of those utilities is the one that rearranges files to speed things up? And maybe more importantly, why is it so critical to keep those automatic updates turned on? These are the kinds of practical questions that show you really get it.
Okay, so we know what software is and what it does. But let's talk about how it's actually made and shared. This brings us to a really big topic in the tech world, open source versus closed source. And honestly, the whole debate, the entire difference, it all comes down to one simple question. Who gets to see the source code?
This table lays it all out pretty clearly. Let's start with open source. Here, the source code is totally public. Think Linux, think Android. Anyone can see it, use it, even change it. The support comes from a community of users. The huge advantage here is that flexibility, but the flip side is that community support can be a bit hit or miss. Now look at closed source. The code is a secret. It's proprietary. This is your Windows or your iOS. You need a license to use it. The big advantage? You usually get professional, expert support and really tight security. The disadvantage, though, is that you're kind of locked in. You can't just go in and tweak the code yourself.
So the really crucial thing to get here is why you choose one over the other. Put yourself in their shoes. If you're a developer, what's the biggest draw of open source? And if you're a giant corporation, why would you shell out the money for a closed source license? Understanding that why is what the examiners are looking for.
Okay, so we've talked about what software is, but how do we actually make it? See, we humans write code in languages we can understand, like Python or C++. But computers, they only speak one language, ones and zeros, machine code. So how do we bridge that gap? Well, that's where translators come in. They're the essential bridge between us and the machine.
So you've got 3 main players on the field here. First up is the compiler. You see this with languages like C++. It takes your entire program, translates it all in one go, and spits out a separate executable file. The big win? The final program runs super fast. Next, you've got the interpreter,
which is what you'd use with something like Python. This one's different. It reads your code line by line by line, translating and running as it goes. It's awesome for testing, but it does mean the program runs slower. And finally, the assembler. This is for the really low-level stuff. It takes assembly code, which is just one step above machine code, and translates it directly. This gives you maximum control right down at the hardware level.
Now listen up, because this is a classic exam question. It's all about how they handle errors. A compiler will read your entire program, and only at the very end will it hand you a big list of all the mistakes it found. An interpreter, though, it stops dead in its tracks at the very first error it hits. And then immediate feedback, that's what makes interpreters an absolute dream for debugging your code. So when do you use which one? It's all about what you're trying to do. If you're testing, debugging, just trying to get things working, you want an interpreter for that instant feedback. But when you're ready for the final release and you need that application to be as fast as possible, that's a job for a compiler. And if you're doing some hardcore programming that needs to control the hardware directly, that's when you'll reach for an assembler.
Okay, let's make sure this is locked in. Which translator is your best friend when you're debugging, and why? And which one is going to give you that lightning-fast final program? The answers are all in how they process the code.
Okay, so we said that compilers translate your code all at once, but that's not magic. It's actually a very specific 4-stage process. And for your exam, you absolutely need to know these 4 stages, what they're called, what they do, and, most importantly, the right order. So let's pop the hood and look inside the compiler's black box.
And here they are. Stage 1, lexical analysis. Think of this as the cleanup crew. It goes through and just strips out all the useless stuff. Your comments, extra spaces, all of that. Stage 2, syntax analysis. This is the grammar police. It checks your code to make sure it actually follows the rules of the programming language. Stage 3, code generation. This is where the magic happens. It takes your grammatically correct code and finally translates it into machine code, the ones and zeros. And the final step, stage 4, optimization. This step looks at that machine code and says, can we make this faster, more efficient, and tidies it up.
Now, trying to memorize a 4-step list during a stressful exam, that's tough. So here is a total lifeline for you. The order is lexical analysis, syntax analysis, code generation, optimization. LSCO. To remember it, just think, lazy students cram often. Seriously, burn that into your brain and you will not get the order wrong on exam day.
Okay, you know the drill. Quick check. In which stage do comments and extra spaces get the boot? That's lexical analysis. And where does the code get checked against the language's rules? That's syntax analysis. You gotta know what happens in each stage. All right, we're on the home stretch now, the final topic. So your program is compiled, but believe it or not, it's still not quite ready to run. See, modern software doesn't do everything from scratch. It relies on pre-written code in things called libraries to add extra features. The very last step of the whole process is linking your code with those libraries.
And there are 2 ways to do this, static linking and dynamic linking. With static linking, the compiler literally copies and pastes all the code from the library directly into your final program file. This makes your program file bigger, for sure, but it also means it's totally self-contained. It has everything it needs. With dynamic linking, it's different. Instead of copying the code, it just puts in a little note, a reference, that says, hey, when you need this function, go look for it over there in that library. This keeps your program file nice and small, and it can even use updated libraries automatically. So the big trade-off is really about file size versus flexibility. Okay, this is it, the final review. You made it all the way through. So let's put it all together. First, can you explain exactly why a statically linked file is so much bigger than a dynamically linked one? And here's one for the top marks. Think about how your choice between open source and closed source software might impact which libraries you're even allowed to use. That's a great thought question. Listen, you've gone through all the core concepts. You've got this. You are absolutely ready for this. Now go in there and ace that exam. Good luck.